Ready?
Oh,
9, 8, 7. Oh, wait. 5.
Hello everyone. Welcome to this virtual learning session where we are coming at you live from Scienceworks. I would like to begin straight up by acknowledging the traditional owners of the land that Scienceworks is on, the Boonwurrung and the Wurundjeri people, and pay my respects to their elders past and present, and also to acknowledge any First Peoples who are joining us today. Of course, Indigenous Australians were the first astronomers in this country, and they have an incredibly rich knowledge that we learn a lot from every day.
Some of the first astronomers in the world, actually.
The first astronomers in the world, there you go. And I better introduce myself first. My name is Kate Barnard. I'm the Science Programs Manager at Scienceworks, and it is my absolute honour today to be talking with Dr Jessie Christiansen. So Dr Jessie Christiansen is an astrophysicist, and she has been called the Tomb Raider of exoplanet research, which I have to say, Jessie, is super cool. So, and we're going to get to talk to you more about that. Jessie works at the NASA Exoplanet Science Institute, and so she searches for, studies and catalogues extrasolar planets. That's planets that are orbiting other stars. So to welcome Jessie, what I'd like everyone to do is to say a big hi, Jessie. All right. So I'm going to get Bridget to unmute you. Not quite yet. I'm going to give you a countdown. I'm going to say 3, 2, 1. Hi, Jessie. Okay. So wait for my countdown. Are you ready to go, Bridget? Okay. All right, everyone. 3, 2, 1.
Hi, everybody. It's wonderful to be here.
Right. Thanks. All right. So just to start up, can I get everyone who has studied planets so far or talked about planets in their classroom, can you put up your hand? All right, lots of people have talked about planets. Yeah, so a lot of us, Jessie, we've heard about some planets. We've heard about planets that are in our solar system, like Mercury and Venus and Earth. Actually, can you put up your hand if you live on a planet? Does anyone here live on a planet? Excellent. I hope everyone is putting up their hands because we all live on the planet Earth, don't we? So we're familiar with the planets in our solar system, but can you tell us, Jessie, what an exoplanet is and why are you looking for them?
What a great question, Kate. So our sun is the star in the middle of our solar system, has 8 planets going around it. I hope you all remember them. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Yes, we got them all. Okay, but our sun, our star, is just one of hundreds of billions of stars in our galaxy. And a lot of them are just like our sun. So for thousands of years, people have been looking up at the stars in the sky and wondering, do they have planets around them too? But it was a very long time before our technology caught up to our imagination. We had to build bigger and bigger telescopes and better cameras in order to find these planets. And in the last 20 years, we've actually found over 3,000 planets around other stars. And those are called exoplanets. So the example that you could see on the screen is another system put right next to our solar system called Kepler 90. So that's the only solar system we found so far that has 8 planets just like us. But you can actually see from the planets that the system doesn't really look like ours at all. That's one of the most exciting things that we've discovered, actually, that most of the planets we found don't look like the planets in our solar system.
Yeah, and I think people have sort of been imagining for a long time, haven't they, like what exoplanets might be like. And now sort of we're getting more and more technology, so we're able to find more exoplanets, those planets outside our solar system, and do some research on them. And so you've been quite involved with doing this research, of course. And one of the missions that is looking for, or that has been looking for exoplanets, is the Kepler mission. Can you tell us, like, what is the Kepler mission, and how were you involved?
Sure. So NASA launched the Kepler mission in 2009. It's a 1-meter telescope in space. So hold your hands out 1 meter apart, and that's the size of the telescope that we're using. The goal of the telescope was to find out if planets like the Earth, so the planet that we all live on, whether those planets were common whether they were everywhere in the galaxy, like every star had a planet like the Earth, or whether they were really rare, that hardly any stars had planets like the Earth. Because 10 years ago, we didn't know the answer to that question. So now we've launched Kepler, and what Kepler did was find thousands of planets around other stars and show us that planets, rocky planets like the Earth with a solid surface, are very common. Most stars have rocky planets around them.
Is that right? So some planets are rocky, like the Earth, like you said, and Mars. Some planets that we know of are made of gases, like Jupiter and Saturn. This is just I've actually always wondered: are there any planets made of liquid?
That's an excellent question. So there is one planet that we found, GJ1214b. I'm really very sorry about the names. They all have terrible names. When we measure the density of this planet, we can tell it has basically the same density as liquid water. So one of the speculations is that maybe this is a water world. So you guys are all too young for the movie Waterworld, but we nicknamed the planet Kevin because it was a water world.
Right. And can you so that sounds like a super exciting planet. I want to go and visit it. But with the Kepler mission, can you tell us more about what your role in that was?
Sure. So Bridget, if you can put up the next slide. Right. So as I was saying, the goal of the Kepler mission was to find out how common planets like the Earth are. So this is a plot showing all of the planets that we found with Kepler. On the x-axis, which is the horizontal axis, it's basically showing how far away from the star the planet is. So Earth takes 365 days to go around our star. On the y-axis, or the vertical axis, we're showing how big the planets are. So you can see Jupiter is up at the top and Earth is down near the bottom. So big planets are at the top, little planets are at the bottom, hot planets are on the left, and cool planets are on the right. Now, the problem is we don't know what planets we're missing. So my role on Kepler, I have been inventing fake planets. I've been simulating, building fake worlds and injecting them into the data. And then we see how well the software does at finding them. And if it misses the planets that I've put in, then we know that we're missing real planets there too. And then we can correct our statistics for the planets we found versus the planets we didn't find.
So you're almost trying to trick the system. Like you've hidden these planets. So we find these planets by looking at the data that Kepler has sent back. And what you've done is like put in some little extra bits of data to see if Kepler finds those bits of data. And then if it doesn't, then we know that it might have missed other planets.
Exactly. And so, yes, it does feel like a trick sometimes. When I very first started doing this, we had a lot of people involved in the process of finding planets. So I wasn't allowed to tell them when I had put fake planets in the data, or they would behave differently. They would classify things differently, knowing there were fake planets in there. So I had to pretend, no, these are all real. So I think some of them got a bit annoyed at me.
But all for the greater good and finding more planets. So can you tell us some more about why Kepler was so important, and what did Kepler find? Because you mentioned that we previously knew about sort of a few hundred exoplanets, and now we know about,
before Kepler launched, we knew about 71.
71, not even a few hundred. You knew 71.
Yes.
And now we
know of 3,700.
3,000.
Yes.
Wow. And so, and the other thing about Kepler is, so it went out and it was kind of finding all these planets. It originally was meant to be sort of a relatively short mission, but it's actually kept going, hasn't it?
Right. So the original mission was supposed to last for 3.5 years. And that was supposed to be long enough to find planets like the Earth. Now, imagine if you're an alien civilization looking at our solar system, then every 365 days, Earth would come around and block some of the light. So that's actually how Kepler finds planets. We measure the brightness of stars over and over and over again and wait for these little dips when planets come in front. So if you were an alien civilization looking at the sun, every 365 days, you would see a little dip caused by Earth. Now, we really want to see 3 dips to be sure that we found a planet, to make sure that it's one planet that's going around every 365 days. So we knew we needed a 3-year mission, and we built in an extra half a year just for redundancy. NASA likes redundancy. It turns out that stars are noisier than we thought. So when we're looking for these little dips in the brightness, we're hoping that the star itself isn't doing a lot, isn't making a lot of noise and changing its brightness a lot. But it turns out that stars actually do change brightness a lot. And we didn't realize this before we'd launched Kepler. We thought our sun was just an average star and the rest of the stars would have about the same amount of noise.
So other stars will change their brightness whether or not there's a planet in front of them.
That's right. So there are things
Wow.
like sunspots. Have you seen sunspots? So these are spots that appear on the surface of the sun and they last for a little while and then they go away again. And sometimes the sun is really noisy. We have these solar cycles every 11 years. They go through maxima where there's lots and lots and lots of spots, and then minima where the sun's really quiet. But if you're actually measuring the brightness of the sun over and over again, you see that solar cycle come out. It's very noisy and then it's very quiet and then it's very noisy and very quiet. And we thought the sun was average, but it turns out the sun is quieter than normal. Most stars are noisier than the sun.
Right, and so of course that's something that you need to take account of in your data, and that's one of the reasons why you want to make 3 observations of that.
Exactly.
Of that dip.
So when we realized that stars were noisier, we realized the Kepler mission had to go for longer in order to find these dips. So we were really excited. We asked NASA for more money and they said yes. And then the telescope broke. One of the reaction wheels, which is basically how we keep the spacecraft pointed in space, actually 2 of them broke. So then we had to go on and do a completely different mission called K2, which has also been an incredible success, but it meant that we couldn't keep doing our original science of finding Earth-like planets.
And so the part of Kepler that broke was the part that keeping it pointed at the right place in the sky.
That's right.
And so then after that point broke, was it just looking like all over the sky?
Well, what it was doing was, so there's 2 ways we keep spacecraft pointed. One is with these reaction wheels, which are basically gyroscopes that are spinning very, very fast, and they keep the telescope pointed. The second way is with thrusters, actual little rockets with fuel in them. And we can use the fuel to point the spacecraft, but there's only so much fuel on board of the spacecraft. So one of the options was that we could go back and keep doing the original science with the very small amount of fuel we had left, but we would run out very quickly. So we decided to come up with a brand new science case that didn't use the fuel in the thrusters and instead used the power of the sun to keep the spacecraft pointed.
Wow, that is super cool. That's some amazing engineering there, like using like the sun's rays to make sure that the spacecraft is pointed at the right point.
Yeah,
in the sky.
The engineers at Ball Aerospace really came up with an ingenious solution. The scientists all thought we were done. We were like, oh, well, the mission's over. Let's go home. And the engineers, were like, no, we can fix this. We can make this happen.
And that they didn't like bring it back down to Earth.
No. So they came up with this new way in space of pointing it using the power of the sun.
It's amazing. Okay, so Kepler, you talked about the fuel that's on board Kepler, and I think you mentioned to me earlier that it's now run out of fuel.
Yeah, just last week we found out that very small amount of fuel reserves that we had has run out, so Kepler is finally done, which is very sad.
Oh, and will it come back to Earth or will it kind of go off into space? What will happen now?
So Kepler's actually quite far away from the Earth. It's actually further away from the Earth than the sun is. And so we're not going to try and bring it back. But one interesting thing that NASA does, once it has an asset in space that it is finished with, it doesn't want anybody else to take it over, any of America's enemies. So we actually have to issue a kill order. Like we have to disable the spacecraft so that no one else could ever log in and turn it back on and use it for something nefarious.
Okay.
So it's been this really interesting psychological thing where all of these people who've been working on this mission for nearly 10 years and trying to keep it alive now suddenly have to kill it.
Oh, it's kind of almost heartbreaking, isn't it?
I know. You get so attached to these instruments.
Well, now TESS is going to build on that knowledge. Right. Can you tell us more about that?
Sure. So Kepler surveyed a very small patch of sky for planets, and it actually went quite deep, quite far away. Most of the planets we found are thousands of light years away, which actually sounds like a long way, but in terms of our galaxy, which is 100,000 light years across.
So a light year, that's a measure of distance, isn't it?
That's right. That's how far light can travel in a year. So our sun is 30,000 light years from the center of the galaxy. And most of the stars we found planets around are about 3,000 light years away. So we've actually explored a very small bubble in our galaxy. A very small amount is what we've explored so far. But on average, they're still quite far away from our point of view. Thousands of light years is still a long way. So the idea of TESS TESS is going to do an all-sky survey where Kepler did a small patch. TESS is doing the entire sky, and it's going to survey all the nearby stars. So all the stars that are a few light years away or a few tens of light years away. So these are relatively nearby. And the exciting thing about those is it means we can study them in more detail. Bridget, if you want to bring up the plot with the histogram on it. Okay, great. So this is a plot showing the distribution of the sizes of planets we found. And basically the thing I wanted to get across with this plot is that there are two peaks. There's two different types of planets we found so far. So there's one peak between the size of 2 and 3 times the size of the Earth. So for context, Neptune is 4 times the size of the Earth. And in our solar system, there's nothing between the size of Earth and Neptune. There's a gap between 1 times the size of the Earth, which is the Earth, and Neptune, which is 4 times. But when we look outside, when we use Kepler to look at the rest of the stars, we see that there's actually thousands of planets in this size gap, and they seem to have this really interesting bimodal distribution. That means there's 2 peaks. There's a peak between 2 to 3, and then there's another peak between 1 and 1.5.
So there's lots of planets that are about the same size as of the Earth, and then there's lots of planets that are between 2 and 3 times the size of the Earth, and then there's less of other sizes.
Exactly, and we don't know why that is. That's a real mystery. So one of the goals of the TESS mission is to measure the masses of a bunch of planets in this size range and work out what their densities are. We want to know whether they're big rocks, like if you just took the Earth and made it bigger, is that what you would see? Or if they're little ice giants like Neptune, if you took Neptune and scaled it down. And where is the transition, and where does it stop being rocky and start being icy and start being gassy? And so that's the goal of the TESS mission. Now that we've got the statistics from Kepler that told us planets are everywhere, now we can start to study them in more detail.
Great. And there's a lot of data, isn't there, that we are going to be able to study with that. One of the things that I think is super exciting about TESS and about all of these missions that are looking for exoplanets is the idea of finding planets that might be in the habitable zone.
Sure.
So can you tell us about what is this thing that we call the habitable zone, and why are we excited about it?
We've only really found life one place so far, which is here on Earth. But it seems like all life on Earth needs one thing, which is liquid water. So going out and looking for places where life might be around other stars, we've decided to concentrate on places where you might have liquid water. So this is the habitable zone is basically the distance away from the star where water could be liquid. So it's not too hot and not too cold. So that's why we call it the Goldilocks zone. So for instance, in our solar system, Mercury is way too hot to have water on it. And out at Jupiter and Saturn, it's way too cold for water to be liquid. The water's all ice out there. But when you have Earth, Earth is just right. Earth is in our habitable zone because the temperature's right for water to be liquid. I mean, there's some places where it's frozen and there's some places where it's a bit steamy, but there's a surface that has water on it. So this is what we're trying to find around other stars. We're searching in their habitable zones to see if they have planets in them that might look like ours.
And so if we find some planets that are in that habitable zone, so they're not too close to the star to be too hot to have liquid water, they're not too far away to be too cold to have liquid water. If we find some of those planets, I know we've already found some that are in that zone, how would we know if there was life on one of those planets?
Yeah, so that's something we're really struggling with right now. What we'd like is to find a molecule in the atmospheres of these planets that could only have come from life. So they're called biosignatures. They could only have a biological origin. Unfortunately, almost everything we've thought of so far also has a geological origin. So like methane you can get out of volcanoes, and water you can get out of, comets delivering water to the Earth. You don't need life. Oxygen you can get from photolysis of breaking up water molecules into hydrogen and oxygen.
Right.
So
none of those would come definitely from life. Like they might come from life, but there's lots of other processes that could have formed them without there being life at all.
Right. So what we're trying to do right now is find the smoking gun, find which molecule or combination of molecules would be very indicative that, yes, this has to have a biological origin. And in the meantime, we're building some very, very big telescopes. NASA is going to launch the James Webb Space Telescope in a few years' time to go and search for those molecules. So we're basically trying to keep up with ourselves, trying to define the molecules we need to look for and build the telescope to go find them.
All right, great. We're going to I've just got a couple more questions for you, Jessie, and then we're going to get some questions from students. So if you do have a question that you want to ask, get ready to ask it. And so we've got about 5 more minutes, and then we'll throw over to some of the folks watching to ask some questions. So I wanted to ask, if we did find signs of life on another planet outside of our solar system, what would that mean for us here on Earth?
Well, that's a really interesting question. I think people would still get up in the morning and make their toast and go to work, but I think it would really revolutionize our idea of our place in the universe if we were able to find life out there. And part of the reaction would be what kind of life it was. It could be that the galaxy is full of simple single-celled microbial life, which is kind of boring from our point of view. Like, okay, great, it's there, but we can't talk to it. If it was intelligent life, it was something that had some information content where we could exchange information, that I think would be far more revolutionary and might actually change the way we live our lives today.
Do you think there's life out there?
Yeah, so I think that I would not be surprised if we find simple life, because, if you look at the time it took for simple life to arise on Earth, almost as soon as Earth was ready for simple life, like had a rocky surface with liquid water, we see simple life appear. But then it's billions of years before complicated multi-celled life appears.
Evolution takes a long time.
Yeah. And we, looking around at all the stars around us that are much older than us, that have planets around them that are billions of years older than us, so far we don't see lots of complicated life.
Right.
So it could be that simple life is simple to make and complicated life is complicated to make.
It's still an exciting question. All right, my last question before we get some questions from the students is here in Australia, and I know you don't live in Australia at the moment. You're living in the United States, but you're from Australia. Are we in a bit of a special place here in Australia to be able to sort of contribute to these missions and to look up at the sky?
Sure, the Southern Hemisphere is definitely the best place to be to look at the sky. We have a much better sky down here than they have up there. We have the Southern Cross, we have the center of the Milky Way galaxy, the skies are generally darker. And Australia is also actually in a really unique position to leverage some of the expertise that have been built up in Australia, especially with like deep space communications, and turn that into, interacting with science missions that other countries are building.
It's an exciting time to be in Australia and be part of this industry. Okay, Bridget, I think we're going to get some questions now from students.
My question is, if you guys find life, when you find life, what do you think will be like? And if it will be anything like humans?
Good question. What is it going to be like when we find it?
It is a good question. I don't have a really good feel for what it'll be like. The exciting thing is, because we don't know what we're looking for when we're out there, I mean, life on Earth all needs liquid water. That's why we're looking for liquid water. But there are other kinds of solvents that life could use. It could be a completely different chemistry that it's based on, in which case it doesn't need to look anything like life on Earth. It can look completely different. There's lots of sci-fi shows out there where the aliens are basically just humans that are green. I don't think that's what we're going to find. I don't think we're just going to find green humans. I think we're going to find something completely different.
Well, it'll be exciting to see what it does look like when we do find it. Oh yeah, here we go. Okay, so the question from Williamstown North is, what is the closest Earth-like planet to our solar north?
Okay, I'll answer the first part of the question. What is the closest Earth-like planet? So the closest star to us is actually a star called Proxima Centauri, which is in the Alpha Centauri system, which again, we can see from the Southern Hemisphere because our sky is the best. So Proxima Centauri is a star it's a 3.8 light years away. So we talked about a light year. It's the distance light travels in 1 year. And it actually has an Earth-sized planet in its habitable zone, which is incredibly exciting. The problem with Proxima Centauri is that it's not a star like the sun. It's a very different kind of star. It's a small, cool red star called an M dwarf. The problem with M dwarfs is that they have much higher UV radiation than our sun does. So you know how you got to put on your sunscreen when you go outside? Well, there's no sunscreen in the world that's going to save you from the UV radiation of an M dwarf. So the problem with the planet around Proxima is we think that it's just being sterilized by incredibly high amounts of radiation, which would be a serious bummer.
All right, thanks for that. We've got a question from grade 334 at CJC. The question is, if we do find life, what will we do?
That's really exciting. So probably the first thing we'll do is to try, if it's intelligent life, we'll probably try and send it a radio message. So we have very, very big radio telescopes on Earth. And we've actually sent out a few blind messages so far where we've just pointed it at the sky and been like, hello, is anybody out there? So if we had somewhere to actually point it, we would probably start by sending a message. And hopefully it's not too far away, because remember, I just said the closest star is 3.8 light years. So it would take 3.8 years for our message to get there, and then we'd have to wait for them to reply. So nearly 8 years. It's a really slow conversation.
Oh, that is a slow conversation. That's even slower than I respond to text messages. Okay, let's go to another school for another question. Is that all right? Caulfield Junior College. All right, can we have someone? We've unmuted you, so if we could have someone from there ask a question, if the teacher could choose someone.
We're having a stargazing night in the next week or two. What should we be looking for?
Oh, that was a good question. So it was a question, if we go out at night to go stargazing in the next couple of weeks, what should we be looking for?
Oh, well, there's a couple of planets up right now, not exoplanets, just planets around our sun, which are stunning. So you should definitely go and look for Jupiter, which will be in the west. After the sun sets, there's a very bright planet up in the sky, and that's Jupiter. And then if you look over in the east, you'll see a red planet, a bright red planet, and that's Mars. And actually, this is the time when Mars is closest to Earth, and you'll see it brightest and reddest. And it's actually confusing some of us astronomers, because we go outside and we're like, oh, wait, that's Mars. It's not usually this bright. So it's a really great time. If you have binoculars or even a very small telescope, just go out and look at Jupiter and Mars. They're beautiful.
Catherine Primary School, grade 5. Okay,
Hi,
can I
guys.
have the teacher at Glen Catherine Primary School pick someone to ask a question, please?
Be on the same
I'm going to do it.
Maybe you can ask, Michael can ask these questions. And I also had a question, how can kids become astronauts or astrophysicists? Looks like a pretty tricky job.
Hello, what's your question?
Why did you disable the telescope when you could have just fixed it?
They sound American.
Who knows?
Oh,
That's a good question. So, Jessie, why you've got a great telescope there? Why did you disable it instead of fixing it?
That is a very good question. The short answer is money. The telescope is very far away. And in fact, it's further away than we have the ability to send people in spacecrafts right now. There have been telescopes that we have fixed in space, for instance, the NASA Hubble telescope, but the Hubble telescope orbits very close to Earth. It's actually just skimming above the Earth's atmosphere every 108 minutes as it goes around. So we don't have to go very far to fix the Hubble, but Kepler is hundreds of thousands of kilometers away. So there's no way we're getting there, unfortunately.
Well, let me ask a follow-up question to that. Why would we, so Kepler's so far away. Why don't we just keep it here on Earth, and then when it breaks, we can fix it?
So we like to go to space because we're trying to measure incredibly small changes in the brightness of these stars, and things like the atmosphere, the Earth's atmosphere. When you go outside and see the stars twinkling, that's bad. That gets in the way of our measurement. And that's just the atmosphere bending the light. The different temperatures of air moving at different speeds changes the direction of the light. The reason why we sent Kepler so far away is because we needed measurements that were so precise that we wanted to get away from the radiation of the Earth's atmosphere and the magnetic fields around Earth. Earth's actually a really noisy place to be. So we wanted to be as far away from Earth as possible to get these very precise measurements. The problem is then we're too far away to fix when something breaks.
All right, we've got another question from Shreya, DECV. What was the first exoplanet that you found?
Oh, okay. So it's tricky to pinpoint this because I worked on thousands of planet candidates before they turned out to be planets.
So what's a planet candidate? Is that like when you're like running for political office and you're like, I'm a candidate for the,
right,
to be the Prime Minister?
So the spacecraft measures the brightness of stars, and we see these dips. But there are other things that can cause those dips. There's all these sources of noise and confusion. So we have thousands of dips that don't turn out to be planets. And in fact, that's what I spend most of my time doing, is working out which dips are real and which ones aren't. So the first planet that I publish, so when we find planets, we write them up and send them into a journal and they get published. The first planet that I published has the very unromantic name of HD 3167D. I'm sorry.
It's not super creative, but
no, it's really not. It was a really interesting planet system though. So we had already found 2 planets in that system and I found a third and published it. I'm really hoping it stays because someone else has published a paper saying it's not real. So we'll see. This is science. This is what happens in science. You make claims and then they have to stand up for the test of time.
you have to defend them. Like, and other people might say, well, hang on a second, we've got some evidence that it's not right.
Exactly.
And
So a different telescope looked at the same system and they saw 2 different signals instead of what I saw, which is 3 different signals. So we're going to find out who's real, who's right.
Okay. All right. Let's go to the next question. Beth in Bali, looking very nice and warm there. Okay, Beth.
What did you expect when you walked into NASA?
Oh, that's a good question. So the question, to make sure everyone heard it, was what did you expect when you walked into NASA? Maybe, Jessie, you can tell us about joining NASA and what that journey was like.
Sure. So I did my Bachelor of Science in Australia and my PhD in astronomy in Australia. Then I moved to America. There weren't a lot of jobs in Australia at the time, and I'm really excited to see that that's turning around recently, and we'll do more in the future. So I went to America and I got a job at Harvard University doing research on what was a NASA project. It was the Epoxy mission, which was a planet hunter that didn't find any planets. I worked on a lot of projects that didn't find planets before I ended up finding planets. So I wasn't a very good planet hunter for a while. And then I was starting to worry about what to do next because I hadn't been successful at finding planets. And I got a phone call from a colleague at NASA who was working on the Kepler mission. And he was like, we have an opening for a staff scientist. Could I get you to apply? And I was like, yes, you could. You could certainly get me to apply. And so I moved out to California and started working on the Kepler mission. Walking into NASA the first day was kind of intimidating because I'm an Australian citizen and I didn't have my permanent NASA badge yet. So I had to be escorted everywhere, including to the toilet, because they didn't want me to see anything I wasn't allowed to see. So I had a big red badge, which basically meant like I was dangerous and shouldn't see anybody's screens. So for the first week, it was a bit intimidating, but then I got my badge and then it was fine.
And now they all know who you are.
Yes,
so now they trust you.
Now they trust me.
Yep. All right. Great. We're going to go to our next school. We've got Wilmot Park Primary School, grade 6. Hello from Craigieburn. Okay. Can I get the teacher to choose a student to come up and ask a question?
My question is, what planet in our solar system other than Earth can humans live on?
So Mars is probably the best option for terraforming, which means changing it so that it could support humans. If you left all of the planets as they were, none of them. But some of them have better options for becoming somewhere we could live. Mars is one. Another really interesting one is Titan, which is a moon of Saturn. It has a really thick atmosphere, and you could actually walk around there without a spacesuit if you just had like a scuba mask. Because the atmosphere is actually thick enough that, you know, your eyes wouldn't bulge out of your head or anything like that. So Titan's another place which is an exciting prospect for the future, but not right now.
All right. So that's a moon, isn't it? So that's going around Saturn.
So that's a moon of Saturn, one of Saturn's moons.
What about our moon? Could we live on our moon?
Our moon doesn't really have a lot going for it. It doesn't have any water, for instance. It doesn't have an atmosphere. It doesn't have a lot of gravity. It's you know, that's where you see the pictures of the astronauts kind of bounding across the moon. It's because the gravity is quite low. So I think Mars would be a better prospect than the moon. It's a bit further away, but
how long would it take to get there?
To Mars?
Yeah.
It depends where you start. You can get there in a few months if you start at the right time in the orbits. Otherwise, it can take years if they're on the wrong side.
Okay, so if a few months is the shortest journey to Mars. Wow. Okay, we got another question from Mildura English Language Centre, grade 3 to 6. So can I get the teacher there to invite someone to come and speak into the microphone?
Okay, come up over here, Ronald. My question, why is planet Pluto, why is not there in space?
Why is it not a planet anymore?
Oh, about Pluto.
Come on, Jessie. We like Pluto. Why isn't Pluto a planet anymore?
Yes, it's a very technical reason, which I disagree with. But if you look at the rest of the planets in our solar system, the other 8 planets, they all orbit the sun in roughly circular orbits, and they're all in about the same plane. So if you imagine the solar system like a big pancake, all of the planets are about in the same plane. Pluto, on the other hand, has a very elongated orbit. It's not a circle, it's a big oval, and it's actually tipped.
That was cool.
Compared to the rest of them. So what happened was we started to find more and more of these objects in the outer solar system that had these elongated orbits that were tipped relative to the rest of the planets. And we had to decide, okay, is this a whole new class of body and therefore we need to give it a new name, or are they all planets? So in the end, they decided to come up with a new designation, which is dwarf planet, and call all of these new things dwarf planets. And then the hard decision was, do you demote Pluto? Do you take it away from being a planet and make it a dwarf planet? And that's what they ended up doing, which is the part I disagree with a little bit, but it was voted on by the International Astronomical Union, who apparently did have the authority to do that.
So it's kind of about definitions, isn't it? Like,
Yeah, exactly. It's still there. It's still everything it ever was, but it's just not called a planet anymore. It's a dwarf planet.
All right, that's great. We've got another question. Lily, DECV, grade 6, Melbourne.
What do you need to do before you go into space?
Good question. So I'd quite like to go into space, Jessie, and I think maybe Lily would too. What do we have to do before we go into space?
So in order to become an astronaut, you have to get selected by NASA. I actually didn't apply because you need to be an American citizen for the NASA astronaut selection process. And then there's a lot of training involved, several years worth before you get into space. So the sorts of people who get selected to be NASA astronauts include fighter pilots, because then you can fly things. You've shown that you know how to fly pilots. Engineers who build things. Scientists who research things and find out answers, but also communicators and educators also have a chance to be astronauts. So there are actually a lot of pathways towards becoming an astronaut, but it is actually a very, very small number of people. I think in the last class they selected 12 people out of 40,000 who applied. So it's a rough trot.
Wow. Yeah. Okay. Well, we'll just have to hope for some space tourism maybe one day. I think I've missed the boat to become an astronaut, but maybe once we develop tourist flights into space.
Oh yeah.
So we've got Star of the Sea, Brighton. Can I get the teacher there to choose someone to come up and ask a question? Hello.
When you send messages out to space, what sort of things do you say and what language do you send them in?
Well, that's it. That's an excellent question, actually, Jessie. You mentioned earlier, like if we did find intelligent life, then we would want to send them a message. But you know, do they speak English? Do they speak French?
Right.
Do they speak Indonesian?
No, it's an excellent question. So the Arecibo message, which is the message I was talking about before, was a message that we beamed out with the Arecibo telescope. And what it actually is, it's basically a series of ones and zeros. The sequence is a multiplier of it's 2 prime numbers multiplied together. So what we're hoping is that an alien civilization understands prime numbers, and that prime numbers are special in mathematics.
So prime numbers are those special numbers that can only be divided by themselves and 1.
That's right. They have no other divisors. So this message that we sent out is a multiple of 2 prime numbers. And if you actually change it into the rectangle that is defined by those 2 prime numbers, it makes a picture. If you make all the ones dark and all the zeros light, it's a picture. So there's several things in the picture. One of the things is a picture of a human, just like a stick figure sort of thing. One of the things is a picture of our solar system, kind of basically saying, you know, the sun, there's 8 planets, I think 9 at the time. And then which one Earth is. There's a picture of DNA, basically showing the double helix structure of the information encoded in our bodies. But it was very difficult to basically define what you send out in these messages. So that's what we came up with. Frank Drake, I think, was the author of that message. But yeah, it's tricky.
I guess one of the things we'd want to do if we were sending out messages is the first thing would be to try and make them understand that it is a message.
Exactly. So having this series of ones and zeros that's repeated over and over again is the first thing. Like, okay, there's a pattern. Okay, this is one sequence. Is there anything special about the sequence? And then hopefully they work out the prime number thing.
Yeah. Okay, this is the very last question. We are going to go to Warren, can I get the teacher there to choose someone to come up and ask the last question?
Okay, so they can hear us, guys. Ryan, do you want to come up? We can hear you.
Okay, what's your question there?
More about the sun, like how old is it and how bright is it, how hot is it, how big is it, stars?
Sure. So our sun is about 5 billion years old. It's a fairly boring middle-aged G star. G meaning it's like yellowish in color as compared to red, like some stars, or blue, like some other stars. Fantastic slide, Bridget. So it's about 5,500 degrees, which is pretty hot, but not as hot as some stars, not as cool. Our star's pretty average. Most of the stars in the sky are smaller and redder, called M dwarfs. So about 75% of the stars in our galaxy are actually M dwarfs. And those are the ones I was saying put out the heaps of UV radiation. So we're not sure about planets around those. But yeah, so our sun's a pretty nice place to be, actually. It's nice and quiet. It's going to live for another 5 billion years. We've got lots of time.
Glad to hear it. We're very happy it's there. All right. Well, I think we are going to need to finish there. Thank you so much. Thank you, Jessie, for such a great conversation. And
thank you, everyone, for calling in.
Well, what we might do is just to finish up, Bridget's going to unmute everyone in a moment, and I'm going to say 3, 2, 1, and I'll get everyone to say thank you, Jessie. Okay. So Bridget's going to unmute you. Ready? 3, 2, 1. Thanks, Jessie, and thank you to everyone who joined today.